About performing CRC checks with linker-generated CRC tables, I'll be using the C2000 MCU code generation tools on Code Composer Studio. Cyclic redundancy codes are a common method of detecting errors that might occur during data transmission. A sender can compute a CRC value and store the value at a location accessible to the receiver. Then, after receiving the data, the receiver can compute the CRC value on the same data and check his or her result against the CRC value that was computed by the sender. If the values do not match, an error has occurred. The receiver can then take appropriate action, for example, requesting that the data be retransmitted. In this demo, I'll show a simple example of the CRC table operator in a linker command file that can be used by a program running on a C28X plus VCU device to perform a CRC check at runtime. Here are the details of the demo that I'll be showing you. I'm running on Code Composer Studio version 6, and I've connected to a 28379D microcontroller EVM board. I've downloaded and installed the Control Suite package, which you can find through the CCS App Center. This demo is a CCS project that has been derived from an existing Control Suite CRC example project. I imported the CCS project from the location listed on your screen. I then modified the main.c file and also the linker command file for the demo. Now we'll switch to the actual demo. This is Code Composer Studio version 6. I've imported a CRC32 demo project from the Control Suite package and renamed it in my CCS workspace. I've modified two files, main.c and the linker command file. Let's look at main.c. You'll note the include of CRC table.h from the C2000 code generation tools include directory. This contains the definition of the CRC table data structure type that the linker will use in generating a CRC table at link time. This is the declaration of the linker-generated CRC table, which allows main.c access to the table at runtime. Below this is the definition of two arrays, test input 1 and test input 2. These are simply banks of data that we'll be performing our CRC checks on. Associated with each array is a data section pragma that instructs the compiler where to define the arrays. Test input 1 will be defined in an input section called test input 1, and test input 2 will be defined in an input section called test input 2. This allows control over the placement of the arrays in memory, as we'll see in the linker command file in a moment. In the definition of the main routine, we'll first do some initialization of the VCU hardware. Then we'll call our CRC checker routine, passing in a pointer to the linker-generated CRC table. We'll get a return value of 1 back from the CRC checker routine if the check passes. In the definition of the CRC checker routine, we'll spin through the CRC records in the CRC table that was passed in. Then, based on the specific CRC algorithm that was used to compute the CRC value at link time, we'll set up the CRC object API that the hardware library uses to call the appropriate routine to compute a CRC value using VCU hardware. Finally, the CRC value computed at link time is compared to the CRC value computed at runtime. If we get through the whole CRC table without a mismatch, then the check passes. Now let's look at the linker command file. In the modified linker command file, I've defined two output sections that correspond to the two arrays we defined in main.c, test input 1 and test input 2. Attached to each output section specification is a CRC table operator which tells the linker to create a CRC record for the output section and insert it into a CRC table object that it must also create. The first argument to the CRC table operator provides the name of the linker-generated CRC table. The second argument indicates what CRC algorithm is to be used to compute the CRC value. In our case, we have two output sections with CRC table operators that use the same name for the CRC table, so only a single table will be created, but the linker will create a separate CRC record in that table for each of the two output sections. The test input 1 section will be checked using the CRC32 prime algorithm, and the test input 2 section will be checked using the CRC32C algorithm. The linker-generated CRC table will also have placement instructions associated with it. The special TI CRC tab output section name can be used to instruct the linker where to place any linker-generated CRC tables in memory. In our case, we put the CRC table in RAM LS3. Now we'll build and run the demo. To run the demo, we'll start a debug session. We're now running our program resting at the start of the main routine. I'll set some breakpoints to watch how the program walks through the CRC checker routine. We hit the resume button to arrive at the top of the CRC checker routine. Looking at the incoming linker-generated CRC table, we see it contains two CRC records. We'll fill part of the CRC object with the location and size of the first buffer of data to be checked. Note that on C2000, the linker computes the size of the data in words, but the CRC object uses byte units for the size of the data buffer. At the next breakpoint, we've detected the first CRC record indicates that the linker used the CRC32 prime algorithm to compute the link time CRC value. We then select the CRC32 polynomial 1 support routine from the hardware support library. When we reach the next breakpoint, the runtime CRC value has been computed, and we can see that it matches the link time CRC value. Now we'll process the second CRC record in the CRC table. This time, the linker used the CRC32C algorithm, so we select the CRC32 polynomial 2 support routine from the hardware support library. Again, the runtime CRC value matches the link time CRC value. So we get a result of run from the CRC checker routine. And we're done with the demo. Here are some additional resources if you'd like more information about CRC checking and using linker-generated CRC tables. If you have questions, I encourage you to check out the CCS and compiler forums